Welcome, Chem 1. Today, we are going to take a look at how we measure things that are really small, more specifically, atoms and molecules. In order to do this, we need to group atoms and molecules together in a larger group, something called a mole, so that makes them a little easier to count and a little easier to do math with. Let's start. Before we get going here, let me just say that you technically already know how to do this math, and you technically already understand the concept. The problem's going to come with, we're dealing with something called a mole that you are not familiar with. No, we're not talking about the ground animal. We're not talking about a secret spy in a covert operation. The mole in chemistry is just a grouping, like a dozen or a ream of paper. So if I say a dozen eggs, you know that that's 12 eggs. And instead of saying 12 or writing 1, 2, you can just say a dozen, which is actually longer than just saying. That doesn't make much sense, right? But a ream of paper is 500 sheets. And so we can use words that make it easier to tell how many we have. This is no different than what we're doing with the mole. 1 mole equals the number 6.02 times 10 to the 23rd. If you look down here at the bottom, counting the number of particles doesn't mean that they have the same mass. If you have a dozen apples and a dozen vehicles, those aren't going to have the same mass. They're simply just the same number of them. And this is important when we get to atoms because different atoms of different elements have different masses. So where does this 6.022 times 10 to the 23rd number come from? It comes from a guy named Avogadro. We actually call this Avogadros number. It's based on the number of carbon atoms in a 12-gram sample of carbon-12 atoms. Why do we use a 12-gram sample? Well, because that's the atomic weight or atomic mass of carbon. And so if we use the atomic masses of all these elements, hopefully we should get 6.022 times 10 to the 23rd atoms in all of those samples. So this basically creates an equality that 1 mole of any element or any substance is equal to 6.022 times 10 to the 23rd particles. Just like 1 dozen is equal to 12, 1 mole is equal to Avogadros number. So because we have this equality, now we can start using that equality to convert from moles to particles or from particles to moles. This can become very helpful when dealing with chemicals in lab settings. Typically, we refer to this as the first half of something called mole mountain. The top of mole mountain is the mole, and the base at one side of the mountain are particles. So if we're going up the mountain, one way to think about that is going up a mountain is difficult, and when you were young, the difficult operation was division. So if we're going from particles to moles, we're going to divide by 6.02 times 10 to the 23rd. But if we were going from moles to particles, we're going down the mountain, and therefore we would multiply by that number. Just remember that the particles side of the mountain, and there's another side, is going to deal with Avogadros number. We'll get to the other side here in a little bit. So let's take a look at a math problem. Once again, this is simply dimensional analysis. You've already learned how to do this. The units are just not as familiar to you. So what's the first thing we do with a dimensional analysis problem? Write down the given. We have 5.67 moles of copper. Get in the habit now of including the unit, moles, and the substance, copper. I know where we're going second semester. If you don't start writing those things down, you're going to have problems. Trust me. Because that's the unit that we are trying to drop out, we know for certain that moles of copper has to go down here at the bottom. Has to. And we're converting to number of atoms. So you could say number of particles or atoms of copper. Either way is fine. And now we simply need a ratio of moles to atoms. Well, how many atoms are in 1 mole? In 1 mole, we know there are 6.02 times 10 to the 23 atoms of copper. We're simply going to multiply 5.67 by 6.02 times 10 to the 23rd. If you were going to enter this into your calculator, this is how I would do it. I'd do 5.67 times 6.02, and then I'd hit the EE button. Remember, we talked about that. EE button, and then I put the exponent, and that tells the calculator that you're in scientific notation, and that should give you the correct answer. You can see that we've set this up correctly, and we also maintain sig figs. The sig figs are going to be based on the given. The given has 3 sig figs, and our answer has 3 sig figs, and that would be atoms of copper. I'm going to start moving through the math a little quicker here. If you need clarification on these things, make sure you ask questions, send me an email, or come see me at school, and we'll show you some more examples. How many molecules are in 0.0034 moles of water? So our given in this case is moles, which means moles is going to be at the bottom, and this is going to be at the top. The only difference here is we're dealing with molecules. Why is it molecules? Because it's water, which is H2O. It's not an atom, but you can see here that it doesn't matter what you're counting, because 1 mole of anything is 6.02 times 10 to the 23rd. I could have said you have 0.0034 moles of donuts, and it would be the same ratio. 1 mole of donuts is equal to 6.02 times 10 to the 23rd donuts. You can see we started with 2 sig figs, we ended with 2 sig figs. We'd use the EE button to type in the scientific notation. This one's a little different because the given is atoms. We have 2.78 times 10 to the 24th atoms of argon, which means atoms are going to be our given quantity, which means atoms are going to go down here, and moles are going to be at the top because moles is what we're looking for. So this is going to be 1 mole over 6.02 times 10 to the 23rd. If we look at the equation here, in this case, we're going to divide. So if I was putting this into my calculator, there's the number of atoms. And then since that's on the bottom, I'm dividing by 6.02 EE23. And that's going to give me the 4.62. If you type it into your calculator this way, it will give you this as the answer. All right? But if you start trying to type in the times 10 to the 24th exponent, order of operations could create a problem and you might get the wrong answer out of your calculator. Here's another quick example of going from molecules to moles. It's the same as the last problem. It's just we're dealing with a molecule, N2O, as opposed to an atom. But you can see molecules at the bottom, 6.02 times 10 to the 23rd, and moles at the top. Wherever you have a particle, which would be an atom, a molecule, or an ion, which we haven't got to yet, those are always going to be associated with the 6.02 times 10 to the 23rd number. Now that we've done those problems, let's take a look at the other side of Mole Mountain. Not only do we know how many atoms we have because we have a mole, we can also calculate the mass because the mole is based on the atomic mass of every element. We call this the molar mass, or the mass in 1 mole of that substance. To determine the molar mass, we've already technically done this. If it's just 1 atom, it's just the atomic mass. If it's a molecule like H2O, we would add up the masses of all the atoms involved, which you've already done to do percent comp. Here's a picture of moles of different substances. This is 12 grams of carbon. This is 65.4 grams of zinc. This is 118.7 grams of tin. Every element has a different atomic mass, and therefore a mole of those substances is all different in terms of mass. So if you're thinking really small about these samples, every one of these samples is a mole. That means they're all the same number of atoms, 6.02 times 10 to the 23rd. But because those atoms are different sizes and have different numbers of protons and neutrons, they're going to have different masses when you have the same number of atoms. So just a quick review here. If I asked you what's the molar mass of oxygen gas, the first thing you would think is oxygen gas is Brinkelhoff, therefore it's O2, and we'd take 2 oxygen atoms and we'd add them together. A little more complicated here. What's the molar mass of calcium phosphate? Well, we have 3 calciums, we have 2 phosphorus, and we would have 8 oxygen. So it'd look like this. We've already done this, and notice the units here are grams per mole. It's because that's how many grams are in 1 mole of that substance. So how can this help us? It helps us complete the other half of Mole Mountain. We've already dealt with particles on one side of Mole Mountain, but we also have mass on the other side of Mole Mountain. As we discussed, if we're going up the mountain toward moles, that means we're going to divide by the number. If we're going down the mountain toward mass or particles, we're going to multiply the number. On the particles side, Avogadros number is what we use. On the mass side, though, the number we're looking for is the molar mass, because it depends on what substance we're dealing with. Mole Mountain can be helpful to people. Some people don't really use it. Just know that 1 mole of any substance is equal to the substance's molar mass, and you can use that as an equality within your equations. So look down here at the bottom. How many moles are in a 45-gram sample of sulfur dioxide? Well, our given is 45 grams. Sulfur dioxide is SO2. And we have grams at the bottom because it's the unit we're trying to cancel out. And we're looking for moles. So 1 mole of SO2 is equal to how many grams? The way we would find that is we'd have to find the molar mass. So if we take 1 sulfur and 2 oxygen and add them up, you would see that the molar mass is 64.0. Remember, we're getting those masses from the periodic table. So in this case, we'd take 45 divided by 64, and that would tell us how many moles of SO2 we have. So if you look at the cleaned up version here, you have 0.7 moles of SO2. Here's another problem. 0.0718 moles of nitric acid, which is HNO3, would have the mass of blank grams. So our given is moles, so that means moles is going to go on the bottom of the equality, and grams, which is the molar mass, would go on the top. And it'll look like this. If we take 1 hydrogen, 1 nitrogen, and 3 oxygen, it's going to add up to 63.0. The importance of labeling is crucial. If you don't label things, it's going to be really difficult to know where to put numbers and what these equalities are. Also notice we have 3 sig figs in the given and our answer has 3 sig figs. So up until this point we've only done 1-step dimensional analysis problems with moles. You have 2 equalities. 1 mole equals 6.02 times 10 to the 23rd particles, and 1 mole equals the molar mass of any substance. But we can use that and tie those together and use moles as kind of a middle ground. You can see this is kind of a simplified version of Mole Mountain with mass on one side and particles on the other side. Why is that important? It helps us do multiple step problems. Let's suppose I wanted to go from the mass of a substance and know how many atoms or molecules were in that substance. How would I do that? Let's go through one. You have a 3.4 gram sample of gold and it wants to know how many atoms you have. So 3.4 grams of gold, the symbol for gold is AU. I want grams of gold to cancel out, so that goes on the bottom. And the first place I need to get to is up Mole Mountain, so I'm going to moles. Now I can go straight from moles down the other side of the mountain. So now I want moles to cancel out, so I put moles on the bottom. And I want to go from moles to what I'm looking for in this case, which is atoms. And so in this problem, I'm going to use both equalities. 1 mole equals the molar mass. 1 mole of gold is 197 grams. And I know that 1 mole of any substance equals 6.02 times 10 to the 23rd. So now I've done a multiple step dimensional analysis problem with both the equalities I have for moles. If we would punch this into our calculator, we would use the EE button here. We would get 1.0 times 10 to the 22nd atoms. So what that means is no matter what sample of any element you have, you can know how many atoms there are by simply doing a mole problem, which can become very helpful once we get into chemical equations and knowing how much product we should produce. We'll get there. Another quick note here, because we only have 2 sig figs in our given, that means we should only have 2 sig figs in our answer. But our equalities here would never go below 3 sig figs. We want to keep at least 3 to maintain some level of accuracy within those equalities. Here's another problem. You got 4.51 times 10 to the 23rd molecules of fluorine gas. The trick here is remembering that fluorine gas is Brinkelhoff. If you forget that, you will say that fluorine gas, if you just say that it's F, that means that the molar mass is 19. But because it's Brinkelhoff, we know that the molar mass is 38.0. That's going to mess up your math. So you have to be paying attention for Brinkelhoff. This doesn't include the formula. It's expected that you know that fluorine gas is Brinkelhoff. So if we look at our equation here, we have our given, which is molecules of F2. So molecules goes down here, and we're converting to moles first. We're going up mole mountain. So here's 1 mole equals 6.02 times 10 to the 23rd molecules. Then we're going down the other side of mole mountain. Moles come here because we need them to cancel out. And grams go up top, which is 38, like I said, because it's diatomic. We do the math, we get 28.5 grams, and that's how much grams of fluorine gas we would have in that many molecules. This last one here is a little more of an advanced problem, but it tests how well you understand the terms being used. If you look here, it says you have this many molecules of carbon dioxide, but it wants to know grams of just oxygen. Well, carbon dioxide is CO2. So if you think about what's going on here, it's telling you how many molecules you have of CO2, but it wants you just to focus on oxygen. So there's another step here. This is kind of a 3-step problem. Think about what's going on. We have this many molecules of CO2. So the first conversion has to be down here at molecules of CO2 because we want these units to cancel out. And the first thing we're going to do is go to atoms of oxygen. And you might be thinking, where do they get those numbers? Well, for every 1 CO2, I have how many atoms of oxygen? 2. So by simply using the formula, we can get to molecules to how many specific atoms within that molecule there are. At this point, we can go from atoms of oxygen to moles, and then from moles of oxygen to grams of oxygen. And that would give us 13.51 grams. Once again, this is a little more of an advanced bonus type problem, but you can see how there's lots of different directions that we can go once we have a good understanding of a dimensional analysis and once we have a good understanding of our mole equalities. And as you can see here, we have 4 sig figs, which means our answer should have 4 sig figs, and it means that we use the Avogadros number that has 4 sig figs in the problem. Listen, I know I just hit you with a lot of information. This is going to take a lot of practice to become experts at it. Keep up the work, make sure you practice this content, ask lots of questions to make sure you understand. I'm proud of you. Good job today. We will see you soon.